Oh, I see. Okay, sorry. Okay, so welcome everyone for today's European Non-Associative Algebra seminar. Today's speaker is Guodong Zhou from East China Normal University, and he will be talking about the homotopy theory of operated algebras. Okay.
Okay. Thank you very much for the introduction. And it's my great pleasure to give a talk in this wonderful seminar. Let me share screen first. So today I will talk about the homotopy theory of operated algebras. So I should explain the notation of what operated algebra. This is just an algebra endowed with an operator. Okay, so this talk will be based on the following papers. So in the first paper, together with Li Guo, Yunnan Li, Yunhe Sheng, we established a complete theory for differential algebras with operator weight. And in the second paper, we finally solved a question by Jean-Louis Laudet. In this paper, we established homotopy theory for differential algebras. I mean, we established the Kozul minimal model and as well as an infinite structure on this deformation complex of differential algebras. Okay, so throughout this talk, I will take a field of character to 0 K. So this talk will have four parts. In the first part, I will take a baby model. That is, I think everyone is familiar with associative algebras. So I just take this baby model to explain our method. So in particular, I will explain formal definitions, combinatorial theory, that is Hochschild combinatorial theory, and also the medium model of the upper part of associative algebras. See the upper part of A infinity algebras. So this is the first part. I think I will spend half an hour even more on the first part in order to convey the main idea or the rough idea of this theory to the audience. Then in the second part, I will talk about, I'll recall some history of differential theory and some philosophy of homotopy theory of algebraic structures. Then the third part is somehow our own work about differential algebras of arbitrary weight. So we will discuss formal definitions and differential cohomology of differential algebras, and we will talk about an infinite structure on the differential complex, and we will introduce the notion of homotopy differential algebras. Finally, we will show that the DD upper part of homotopy differential algebras is exactly the minimal model of the upper part of differential algebras. In the course of proof, one can find the Kozul homotopy copilot of this. So in the last part or the fourth part, if time permits, I will talk about our related work on other operated algebras such as Rota-Baxter algebras, embedding tensors or everything algebras, and non-Associative algebras. So let me begin the first part, which is the introductory part. I will talk about the so-called homotopy theory of associative algebras. In fact, this page is somehow the panorama of the story. So the story will begin with the milestone work of Haber in 1963 and 1964. In these two papers, Haber studied formal definitions of associative algebras. From this, he invented a complete theory. But this complete theory is not new. This is essentially the so-called Hochschild cohomology theory, invented 10 years ago. But anyway, he considered the Hochschild complex as a deformation complex of associative algebras. And more importantly, Haber found a differential differential graded Lie algebra structure on the Hochschild constraint complex. So it is this DD Lie algebra which control deformation of associative algebras. So this is the first part of this theory, and the second part is the work of Jim Stashev in the same year, in 1963, in 2 papers published in Translation AMS. Stashev introduced the so-called A-infinity algebras, or strong homotopy associative algebras, if you like. So, but the story is not going to its end, because formally you can consider A-infinity algebra as a higher homotopy version of associative algebras, but there is no theoretical proof of this fact. So from an operatic viewpoint, it was Ginsburg and Karpov in their foundational work on constraint duality for operads. They show that in fact the operad of A-infinity algebra is actually the minimal model of the operad of associative algebras. So they complete the picture. Okay, this is just a general picture. Let me begin with the notion of associative algebras. I think everyone knows very well about it. Okay, I should beg the organizer to forgive me. I will talk about always associative algebras, although this is a seminar for non-associative algebras. I'm sorry. Okay. So associative algebra is just a case vector space endowed with multiplication. Everyone knows that. But we ask that this multiplication or binary operation satisfy the associativity associum. So this is, we see that A times B times C equal to A times B times C. Okay, but in terms of maps, you have this formula. Notice that in fact this formula is something quadratic. You know, we use mu twice in each term. Okay. So what from the definition of associative algebras? This just we want to deform the multiplication effect. We also introduced a small parameter, but in algebra usually we use the formal power series. So let us giving an associative algebra A. So let us consider this big space A double bracket T. This is just the formal power series with coefficient in A. Okay, so we want to establish associative product on this space, but we ask it to be K double bracket T bilinear. Okay, so by some consideration of very easy consideration, we see that such a product is determined by mu T, which is a map from A tensor A to A double bracket T. So in fact, this mu T is a sequence of from point theory of some maps mu I, where mu I is just a bilinear map. Okay, so if mu 0 is mu, we see that mu T is a form of deformation of mu, and mu 1 we'll call the derivative or infinitesimal of the form of deformation mu T. But why is it important? So what we ask is exactly, so the associativity of mu T. So this is the formula for this associativity of mu T. But from power series, you can collect collection of T power n and compare both sides. So this means that for each n, you have such equations. Okay, we will call these equations deformation equations. So for example, if n equal to 0, sorry. So this is just the original associativity for mu 0. Okay, but for n equal 1, you will see a formula which is a little more complicated. But if you are electric, you will guess this is a formula for differential of mu 1. This means that mu 1 is a certain co-cycle for a certain cohomology theory. Yes, it is. This is exactly the Hochschild cohomology theory. So let me recall something about Hodge cohomology theory. So given associative algebra A with together with bimodule M, so the Hodge complex is defined to be as follows. So the Cn is just the space of linear maps from A power n to M, and you have a so-called Hodge differential. Maybe these formula are different from the Euro ones because I modified some signs. Okay, that's not so important. So anyway, so this form complex and the cohomology groups are called the Hodge cohomology groups of the associative algebra with coefficient in this bimodule M. Okay, so maybe these formula are rather complicated. Let me consider G to be in C2. This means that the G is mapped from A times A to A. So what's the differential of G? One can write down it explicitly. So return to our deformation equation of mu1. This is just this equation. So this equation equivalent to saying that mu1 is the Hochschild cocycle. So let me return to this deformation equation. So once you can deform something, you obtain a deformation equation. If you are clever enough, you can guess a cohomology theory, such that this mu1, this is infinite dilemma, should be a cocycle for certain cohomology theory. Okay? But we have more structures, the so-called Gas-Hammerly bracket. So there's something wrong here, in fact. This bracket is, will be such a map like this. So from Cn times Cm to Cn plus m minus 1. So somehow the degree are wrong. No, that are not important. Let us explain the bracket. So in fact, if you have considered f to an n quotient, g or m quotient, then the Gaussian bracket of the f and g will be n plus m minus 1 quotient. Its definition is rather complicated. Even up to now, I think this is true or false. Okay, anyway, I should say that there's a Lie bracket somehow with wrong degree. Okay, if you like, I can give you some examples. For example, if n equal to 1 and m is equal to 0, f is just a linear map from A to A, and g is zero quotient, so this is the element of A. So the Lie bracket is just something like the abbreviation of f at A. Okay, so if A and M are both 1, so f and g are linear map from A to A, then the Lie bracket is just the composition of f and g minus the composition of g with f. Okay, so for n, m, both 2, mu and mu j are bilinear form, bilinear functions on A, so their Lie bracket is something complicated. But don't worry, this is something I should say. Okay, the Lie bracket is in wrong degree. So somehow to state the results properly, I need some shift. Don't worry about this technical detail. Just take a shift. So the milestone result of Gas-Haber says that in fact the Hodge-Cauchy complex with a shift is in fact a differential differential grid Lie algebra. Maybe someone doesn't know what a Lie algebra is, so let me recall this definition. Okay, the differential grid Lie algebra is just a grid space together with two operations. The first one is the differential of degree -1, of course, and the second one is the Lie bracket, in fact, at degree 0. And we also furthermore that the differential is the derivation for the Lie bracket. So this is a very very well-known notion, if you like. Okay, but one thing I want to recall is something like this. So an element of degree -1 is a Montagnan element if it satisfies the so-called Montagnan equation at 1 alpha minus 1 over 2 L2 alpha tensor alpha equal to 0. Okay, so the importance of Morgan elements is something like this. So suppose you are given a DTD algebra, then a Morgan element can be twisted this DTD algebra to obtain a new DTD algebra. Okay, by a certain twisting producer. Okay, just remember this. So it means that once you have a Morgan element, you can twist original DTD algebra to obtain a new DTD algebra. Okay, that's a key point. Okay, now let's return to the Gauss-Hamilton algebra. Recall that for vector space, I define this rather complicated space maybe, but remember it. If V is a social algebra, this space is just the underlying space of the Haucher chain complex. Or maybe there's something complicated here. You have some shapes. That's not important for my talk. Okay. Anyway, so I have three facts which are important. Okay. The first one is even if V is just vector space, this means the ungraded ones considered as concentrated in degree 0. In fact, this space is still Lee algebra endowed with the Gauss-Lie bracket. This means we can throughout the associative algebra structure, the definition of Gauss-Algebra still works for vector space, not just for associative algebra. So, but as I told you that Lie algebra has a notion of Morgan element. Let us consider Morgan element in this Lie algebra. A very interesting fact is the set of Morgan element in this Lie algebra is in function with associative multiplication of V. Okay, this means that for the space V, if you want to define a structure of associative algebra, then this is equivalent to say that you are given a Morgan element in this Lie algebra. Okay. The second fact is something like this. So let A be a associative algebra. As I said in the second fact, that mu is in fact is a Morgan element in the Lie algebra. So remember this. Remember that in fact for Morgan element, you can twist the original Lie algebra to a new Lie algebra. So we can twist original space, the original Lie algebra by this Morgan element. We will obtain a new DT algebra. The third fact says that in fact this underlying space of this new DT algebra is just the Haucher complex. And this, of course, this DT algebra is just exactly the Gauss DT algebra we described before. Okay. So if in a word, this theorem gives a Guodong characterization of associative algebra structures on vector spaces. Okay, so in fact, this result holds for vector spaces. What happens if you replace V by a graded vector space? So let me give the setup. So it's the same thing as before. Although I use the tensor algebra, something like this. Don't worry about it. This is just the space of Haucher complex. Okay. I mean that for graded vector space, this space is still a Lie algebra, in other words, the Gauss-Lie bracket. But at this time, what are the Morgan elements? Yeah, very good. So by technical condition, we need to take a reduced version of this Lie algebra. But Morgan element in this Lie algebra or reduced version of the Lie algebra, in fact, is exactly the so-called A-infinity algebra structures. So what I mean, if V is an ungraded space, then Morgan elements in the Lie algebra are associated algebra structures. But if V is graded, then Morgan elements are just A-infinity algebra structures. So if you write down the Morgan equations, so A-infinity algebra structure on graded vector V is a sequence of maps of Bn from SV tensor n to SV of degree -1 satisfied in Morgan equation. But if you delete this shift S, you can write down explicitly the Morgan equations. We will obtain this definition of A infinity algebras. So A infinity algebra structure on a Guodong space V consists of a family of operators Mn, which are degree n minus 2, and which satisfies so-called star-shaped entities. So these entities are introduced by James Star-Shaped in 1963. Okay. Of course, these equations are rather complicated. Well, consider small cases. So for n equals 1 means that M1 is a differential. So remember that for A infinite address, M1 is always differential. For n equals 2, this means that M1 is the derivation with respect to the multiplication M2. But for n equals to 3, we want to show that M2 is something associative, but that's not true. But it is true up to homotopy. For example, consider this formula. So this part is just the associative for M2, but it's not 0. So there is some defect. This defect is just a differential of F3 up to size. So we see that M2 is associative up to homotopy. So from this definition, you can say that Star-Shaped should find the right definition of homotopy version of associative algebras, but this is not theoretically this is not true, in the sense that you should prove the DGR part of A infinite algebras is the mini model of the upper part of associative algebras. So I guess some people in the audience don't know anything about the upper part. I will give a crash course on upper part. I will not go into the details, but okay. So operads theory is a tool to describe algebraic operations. Roughly speaking, operads is a sequence of spaces Pn, where Pn is considered as a space of n-ary operations. So, and we ask that we have some composition of operations and we have some associations. Okay, let me give you an example. That's the most important example maybe. So let V be a vector space. The automorphic operator on the V is defined to be what? So on the Vn, it's just the space of linear map from the V power tensor n to V. This means that the space of n linear maps on V. And for two maps F and G, we can define so-called partial compositions as using this formula. So maybe this is rather strange things, but usually we can present everything in terms of trees. Okay, so an n-ary operation, oh sorry, this is a typo here, this is n. So will be presented by a corolla with n input and one output. So this is in fact this is a tree, plane routing tree, okay, with n input and one output. Okay, so for the partial composition, I write a rather complicated formula, and it's a tree presentation. Okay, this is F circle 1, T, circle 3, H, circle 9, K, and circle 10, L. So you can see this is this ternary operation were represented by this tree. Okay, I hope this will help you understand the situation. Okay, so for algebra, you have notion of a P algebra. So this is just a upper map from P to on V, the automorphic algebra of V. So somehow a P algebra is a representation of P. Okay, for example, let us consider the L part of associative algebras. Recall that associative algebra is just a vector space with the associative binary operation which satisfy the associativity axiom. Okay, the upper part of associative algebra is defined to be quotient by a free upper part by an ideal. Okay, so the free upper part is generated by mu. In fact, mu, you know, this is a binary operation. and I is generated by the associativity. Okay, so I will explain something about the free operand. So anyway, so associative algebras are exactly the so-called algebras over this operand ASS. Okay. For example, the A-infinity algebras are just algebra over the A-infinity operand. Okay. So present mu as a corollary with two leaves. Then each element of Fm, the free operand, will presented by all possible composition of mu. So if you can imagine, in fact, each element is presented by a plain binary rooted trees like this. Okay, so in fact, the free operand Fm has a very space, is a very space generated by all these trees. Okay, and the associativity axiom will present like this. So you have a left comb and the right comb. The difference is just the associativity axiom. So you should divide this ideal. Okay, so each element of in ASS can be presented by a so-called right comb because the relation is you turn a left comb to a right comb. Okay, in fact, we can prove that in fact this presentation is unique. So everything in ASS can be presented by a unique right comb. Okay, let us consider the DT operand of A-infinity algebras. Okay, consider the Starship identities. Okay, which is rather complicated. But remember that M1 is differential. M1 is differential. So let me write down the differential of Mn. Because Mn is the element in home V tensor Vn V. So since V is a complex with differential M1, so this whole space in fact is complex. So you can take the differential of Mn. It is defined as this formula, but the Starship identity can be expressed as the partial Mn equal to such things with some signs. Okay. Let me present this graphically. Draw Mn as a corolla with n leaves, but now you know n at least 2. M1 is the differential, who is part of the underlying space. Okay, the Starship identity will be printed like this. Okay, so the differential of Mn is something like this. Okay, so to conclude the story, Ginsburg-Kaplan proves the following things. So the first thing is the DTR part of A-infinity algebra. It is easy to see this is a free grid algebra generated by Mn with degree n-2, endowed with the above differential. Okay, and it is easy to see, in fact, that the operator map from ASS infinity to ASS, which send M2 to mu, but for higher multiplication, MK sent to 0. But this operator map is a Gaussian isomorphism. So in the sense of operator theory, we see that in fact this operator ASS infinity is the minimal model of ASS. Moreover, in fact, Ginsburg-Kaplan established the Kozul duality theory for operator. They show that in fact the operator ASS is a Kozul operator. I would not want to introduce the notion of Kozul operator, but ASS is something quadratic. And I say that, in fact, you know, here, this relation is something quadratic. So if you know something about Kozul algebra in algebra, in relativity theory, you know, then the notion of quadratic algebras and the notion of Kozul algebras, something like that. The notion of Kozul dual coalgebra, something like this. So in operator theory, we can also express such a theory. So for example, AS is a quadratic operator. In fact, it's more. There are more. AS is a Kozul operator. It has a Kozul dual cooperads AS and shrink. If you consider this callback structure of this ASS and shrink, which is exactly the DDR part of A-infinity algebras. So until now, in fact, Ginsburg-Kaplan prove that the DGR part of infinite algebras is actually the minimum model of AIS. Okay. Next, I want to explain to you that in fact, from operads theory, one can recover everything discovered by Stashev and Gasharbur. Okay. Now I see that AIS is a Kozul part, so it has a Kozul dual covariant. It has anti-shrink. So for vector space, you can conform this home space. You can consider this one. It has anti-shrink is a co-algebra, and other V is an algebra. So you have a convolution product. Somehow this space has a structure of algebra. Okay, in this case, it's a structure of Guodong Zhou. So somehow you have a Guodong algebra because this is a product. Somehow you can take the commutator. So this space becomes a Guodong algebra structure. In fact, it's not difficult to show that this home space is isomorphic to the Gasharbur-Lie algebra we mentioned before. And I repeat these two facts in this theorem. So I mean the set of market element in this Guodong algebra, or this in his home space, in bijection with associated algebra structure on V, and for algebras for associated algebra, you can twist it, the old DG algebra to obtain a new DG algebra whose underlying complex is just differential complex or the Hochschild quotient complex of A. Okay. So far so good. So in the first part, I take associated algebra as a BB model to explain the story, the work of Gasharbur, the work of Stashev, Gilbert-Harpumov, and also another story of Konchevich-Sambolman, how to produce everything from operads theory. Okay, so yeah, so far so good. Half an hour. Okay. So in the past part 2, I will recall some background. So in 1945, Hochschild introduced a complete theory for associated algebras. But as I said before, in fact, the milestone struts were discovered by Gasharbur and Stashev. And later, Nahas and Richardson investigated deformation and complete theory of Guodong algebra. And in 1990, Jim Stashev, motivated from works of physicists, introduced the so-called infinite algebras. Infinite algebras are just homotopy version of Lie algebras. And infinite algebras are the right tool to describe differential theory. Okay, so in the 90s, Bertolini proposed a conjecture about operator action on Hochschild quotient complex. He thought that the little disc part will act on the Hochschild quotient complex in some way. Okay, and another big work is the work of Kozul, and also another proof by Tamaki. Okay, the philosophy of deformation theory after many work. So this sentence is taken from a letter by Bertolini. It says, in fact, the deformation theory of any mathematical object can be described starting from a certain DG algebra associated to the mathematical object in question. Okay, so this is the philosophy of modern algebraic deformation theory, and this theory has been put into a real theorem by Lurie and Predan in characteristic zero by using the so-called infinite category. Okay. Now let me mention two big problems in differential theory. So consider we are given an algebraic structure governed by part P. I mean that we want to deform P algebras. So the first problem is to define the deformation cohomology of P algebras and describe the DG algebra or a infinite structure on the deformation complex. And the second big problem is find the optimal version or minimum model of P infinity of P. Okay, we will see that for Kozul, this question has very simple answers, or at least not simple. Maybe you have a theory to do it at least. Okay, when the operator P is Kozul, in fact, I take associative algebra as big model before. This operator is Kozul, and the commutative associative algebras, Lie algebra, Poisson algebra, Pre-Lie algebra, Leibniz algebras, and also Lie triple systems. These operators are all Kozul. And for the second problem, we want to find a minimodel or observation P infinity. As I said, for Kozul operator, it is a quantity operator. You can define the P and shrink, which is a Kozul dual cooperator. You just take the copart conversion of this Kozul dual cooperator, which is the P infinity. And the general theory of Ginsburg, Karpov, and developed also by Kessler and Jones shows that, in fact, this P infinity is just a minimodel of P. This means what? This means that you have a Gaussian isomorphism from P0 to P, something like this. Okay. And for the second problem, first problem, you want to describe the differential complex and realize its DDLA or algebraic structure. This theory, as explained by Kozlovich, Berleman, and someone else, I explained just like this. Okay. So giving a Kozul operator P, just now I said that you have a medium model P infinity, which is defined to be the compact structure of P and shrink. So the differential complex is just this home space P and shrink, home P and shrink on V, but maybe you need to twist it something. Okay, this is the differential complex. And in this case, we will see that in fact, on this complex or on this space, you have a structure of DG algebra. Okay, so if you know well about the Kozul duality theory for operator, then for Kozul operator, we have everything. But the problem is we have many non-Kozul operators. For example, the operator of Rota-Baxter associated algebras, Lie algebras, the operator of differential associated algebras of non-zero weight, homo-associated algebras, homo-Lie algebras, etc. What's the key difficulties in this case? The problem is first one, the P and shrink. So in fact, in this case, we don't know what's a P and shrink. So this, if you know something like this, P and shrink, so it is not a cooperative, but a homotopy cooperative. If you don't know operator theory, I should say that in general, we think that P and shrink is a coalgebra. But here, it is not coalgebra, but an infinity coalgebra in every algebra, like this. Okay, and we also don't know either the differential complex like this. But as I said here, for Kozul operator, this complex is a DG algebra. But for non-Kozul case, this complex is not a DG algebra, but a genuine infinity algebra. So in non-Kozul case, there is no general theory so far. How can do? In fact, this story is rather interesting. We return to the original method of Kessler. This means that we consider formal dimensions, we guess a dimension complex or complete theory, we guess a structure of an infinite structure on the dimension complex, and from this we can guess the minimum model. Of course, it's not an easy task, but anyway, there's something can be done. I think the first breakthrough is done by Rong Tang, Chen Mingbai, Li Guo, and Shen Yunhe Seng. Sorry. In this paper published in Communication Metaphysics, in fact, they invented a complete theory for relative Rota-Baxter algebras, Rota-Baxter operators. Okay, but their methods are using the so-called divide bracket technique. And the second paper also deals with relative Rota-Baxter algebras. And in the third paper, they consider embedding tensors, or if you like, averaging Lie algebras. And in these two papers by us, we consider differential algebras, which is the subject of this talk. And in last paper with K1, we finished the homotopy theory for Rota-Baxter algebra. Okay, anyway, there are many cases could be done. Okay, so let me remind you what's an infinite algebra. So this is a generalization of DD algebra. So you don't just have a differential Lie bracket, you have a high Lie bracket as an Ln, satisfying some property like Stokes symmetry and higher Jacobi identities. So these are rather complicated formulas. Don't be afraid of them. Okay. So for example, L1 is always differential. L1 is the differential for L2. But L2, we thought that it is a Lie bracket. No, it is just a Lie bracket up to homotopy. Okay. And you have also had the story of Mahogany element in Lie infinite algebra. You have also had the twisting producer, but the formula are rather difficult to state. Okay. In the remaining 20 minutes, let me explain our main work on differential algebras. So, a differential algebra of which lambda is an associative algebra together with the linear operator dA, which satisfies this somehow modified differential equation. Okay, so let me give you some examples. So derivation in calculus is just a differential operator of weight 0. So you don't have this bizarre term. Okay, lambda just 0. So this is just 0 the derivation. But for example, if you are learning calculus, when lambda is not 0, you have this formula, the differential quotient. So it is easy to see that in fact d lambda f is just a differential operator of weight lambda. And also there are some examples in numerical analysis. The forward and backward differential operators are just a differential operator of which minus or plus or minus 1. Sorry. So this notion, general notion of differential algebra of arbitrary weight was introduced by Li Guo and Kaiger. Okay. Here is a remark of Jean-Louis Laudet. The defining relation of different operator of any weight is given like this in terms of maps. So consider this relation. So for example, this term has degree 2, you use 2 operations. But this term are degree 2, or you have only 2 motion. But when lambda is not 0, this term has uses 3 operations. So it is a term of degree 3. So if lambda is 0, in fact, Laudet shows that they are part of differential algebra, of which 0 is Kozul. But when lambda is not 0, since you have a term of degree 3, this is not a quadratic relation. So the operator is not Kozul. Okay. So in 2010, Laudet raised the following question. He asked to develop new techniques to extend the Kozul duality to with no zero case. Okay. In fact, in our work, we completely resolved this question of Laudet and developed the homotopy theory of Kozul duality theory for differential algebras of arbitrary weight. Okay, let me begin. In fact, our methods are rather naive, following the philosophy of Gasthaber. We consider formal definition first. So let me be very easy thing. Let me begin with very easy things. So let A be a differential algebra. So we just deform the differential operator and leave the multiplication mu A unchanged first. So you have a 1 parameter formulation of differential operators, just as I explained for partial cohomology. So the condition is that in fact your dt should rectify the equation like the differential defining relation for differential operator. But here the problem is that this mu t is mu a. You don't have higher multiplication. You don't have other mu1, mu2, something like this. So, okay. You have this condition here. You can understand here if you have, okay. So consider the case n equal to 1. Our deformation equation will be of this form. So this is a rather strange formula, but following our experience about for deformation of algebras, this equation should mean that dy is a cocycle in a certain combinatorial theory. That is okay. So a very interesting fact about this is for differential algebra and for differential bimodule, you can guess the definition of this notion. Okay, one can define a new differential, a new bimodule structure on M like this. Wait, it's strange, but it's interesting. Okay, let us consider the differential equation. Yeah, I mean this one. So if you use this new action, you will have this. Yeah, if you are familiar with Haucher complete theory, this means that what? This means that in dy is a Haucher cocycle, but for what? For A, with coefficient this new bimodule. This tweeted by
Excuse
new
me,
bimodule.
can I ask a question?
Sorry, yeah.
Sorry.
Please.
Yeah.
What's your question?
So when you say M is a differential bimodule, right?
Yes.
Yeah. So my question is, M is a differential bimodule, right?
Yes.
So what does it mean actually? Because you see in the differential algebra of weight lambda, so it means it has to be also weight lambda, right? Differential bimodule.
Yeah. You have a differential on M. Here, look at this notation. Okay, so you replace A or B by an element of M. Yes. M is the bimodule.
I see.
With,
okay, with weight lambda.
With a linear operator dm satisfying an equation of this form. Yes. So you can guess it's very easy to guess. You
right?
Okay.
I see.
Yes.
Okay.
Yeah. Thank you.
Mm-hmm.
Okay. So this differential equation is just the same thing as d1 is a Haucher cocycle, but in the Haucher complex of A, with coefficient in the new bimodule, not the old one. A. This is the new bimodule. So from this, you can guess the complete theory for differential operators. So given a differential algebra of which lambda and M is a differential bimodule, you just consider the Haucher complex of A, but with coefficient in this new bimodule M. This complex will be called the Cauchy complex of differential operator, with coefficient in the differential bimodule M. And its cohomology is called the cohomology groups of differential operator. But it's not the end of the story. So just now I only deformed the differential operator. You can deform at the same time the multiplication and the differential operator. Okay, so now mu t and dt will satisfy more equations. And you can calculate the coefficient of t power n, and you can compare something. You will have these two equations. Okay, the first one we meet before. Okay, and the second one is complicated. Anyway, consider the case of n equal to 1. Okay, the first one means that mu1 is a Haucher cocycle, and the second one is strange. The left-hand part is just the Haucher differential of d1. No, sorry, the differential of d1 in the Cauchy complex of differential operators. But the right-hand side is something related to mu1. Something related to mu1. So now you should guess, in general, the complex. Okay. After some time, we found a tree map. Okay, from the Haucher complex of A with coefficient in M to the Cauchy complex of differential operator. Then this is a tree map, which is defined like this, which I don't want to explain. It's just a formula. And if you return to the case n equal to 1, I mean, these two equations. Okay, so we will see in fact the first one is just mu y the Hodge cocycle, and the second one is this formula with this tree map phi got involved, and the deformation equation in case n of y, it just says that in fact something like this. Oh, I haven't defined this one. Okay, let me see. The negative shift of the mapping coin of this tree map is defined to be the constraint complex of differential algebra. And this cohomology called the cohomology groups of differential algebra. Okay, this is some strange maybe, but anyway, from the dimensions we can guess a cohomology theory. Yeah, maybe it's wrong. But anyway, in the second paper, we consider something like this. Okay, consider for a vector space V, we define a vector space like this. So this is direct sum of algebraic part and differential operator part. So this part is just a Hodge complex. Yes, we understand this part as a Hodge complex, and this part is space of Cauchy complex of differential operators, in fact. But anyway, we found the following result via hard work. Okay, given a greater space, then on this space there's a infinite structure. When we restrict this infinite structure on this algebra part, this will give our constructible greatly algebra. I'm sorry, I cannot give the explicit formula of this algebra structure here, but it's rather complicated. But anyway, this is the right infinite structures to be. Why? It's okay. The first theorem says, let V be a good space. Then, in this new infinite structure, Mohagat elements are in bijection with differential algebra structure of weight lambda of V. Okay. Now, if you are given a differential algebra, then this differential algebra structure corresponds to a Mohagat element alpha. You can twist it. You can twist the original algebra by this alpha. Then we get a new algebraic structure. The algebraic complex of this twisted version can be shown to be just the Cauchy complex of the differential algebra. So this term justifies that our infinity algebra should be the correct one. Should be the correct one, but we are lack of an open-headed proof still. Anyway, so let us define homotopy differential algebra. So this is a Mohagat element in a reduced version of our infinity algebra. Okay. Anyway, I can give you the definition. So homotopy differential algebra is just a vector space with the vector space with two family of operators Mn, which are called higher multiplications, and Dn, which are called higher differential operators. So subject to conditions. The first one is the structural identities, and the second one are called higher differential operator identities, if you like. So this is something rather complicated. I don't want to be very explicit. Okay. Anyway, if you consider small n, for example, D1 is just a tree map, and D1 is a differential operator of weight lambda, sorry, with respect to the multiplication M2, but only up to homotopy. So this part, if it is 0, this means that D1 is differential operator with respect to the multiplication M2, but it's not 0. So there is still a defect part, which is the differential of D2. Oh, anyway. Finally, we can prove something like this. Let us consider the DT part of differential algebra. Then we can show that it is a free part and denoted with the differential. And this DDR part is a mini module of the L part of differential algebra of with lambda. This means that we finished at least the answer to this question. Okay. Anyway, in the cost of proof, one can introduce the Kozul dual of this L part, such that its compact fraction is just the DDR part of homotopy differential algebras. But this Kozul dual, it is only a homotopy copart. It's not a copart. Okay. So maybe I can present this DDR part more graphically. So higher multiplications are presented by corolla with black roots, and the higher differential operators are presented by corolla with white roots. Then the differential will given like this. So the first one always touch up identities, and the second one is the higher differential operator identities. Okay. So far so good. Okay, I have still 5 minutes. It's enough. Okay. So let me mention some related work about other operated algebras. So maybe many of you are familiar with Rota-Baxter algebras. So given an associative algebra R, a linear operator is called a Rota-Baxter algebra with lambda if we satisfy this equality. And also you can define the so-called relative Rota-Baxter Lie algebra. So this is a Lie algebra T and representation of T. And T is a linear map from this representation V to G, satisfying this property. So this is a so-called relative Rota-Baxter Lie algebra, of which 0, in fact. Okay. Anyway, for this kind of absolute or relative Rota-Baxter associative or Lie algebras, we can define the deformation complex and construct the L-infinity structure. We can also define the operative version, I mean the homotopy Rota-Baxter algebras. So in a series of papers, okay, so I mentioned before work of Tang, Bai, Guo, Sheng, Ref, Seng, Tang, and also our works. And also there's a preprint in prepared reason. We want to establish the homotopy theory of Rota-Baxter Lie algebras completely. And we can also prove the mini model, okay, for Rota-Baxter associative algebras and Lie algebras. So the story is complete for Rota-Baxter. And for every algebra or Humanity testers, every algebra means the associative algebra with together with the Arrhenius operator, which is rather strange, I don't know. Okay, for Lie algebra, you have also the so-called relative version. You have Lie algebra VD, and you have a representation V of G. Then a linear map A from V to G is called Humanity testers, if we identify something like this. Okay, so for every algebras or Humanity testers, we can define differential complex and L-infinity structure. For example, in the first paper, we deal with everything associated algebras. And in the work of Seng, Tang, and Cheng Chang, they consider Humanity testers, or if you like, everything Lie algebras. But I should say that the open problem here, we cannot prove the mini model. The rough reason is there's a Fourier sequence which is divergent. Okay, so another structure is the so-called knockout algebras. So this is a three algebra together with a knockout operator like this. So in a joint work with Cao Shong, Kai Wang, Yuan Zhang, we find in fact we can define differential complex for knockout algebras. We can also construct L-infinity structure and introduce the homotopy knockout algebras. We can also prove the mini model, and we found some application to the so-called knockout geometry invented by some Russian guys, which I don't know. Okay. So maybe time is over. Thank you very much.
Okay. Sorry, my internet is not so stable, so I probably will not turn on my video. So, are there any questions, comments about this talk? Can I ask you this question? So you mentioned that. Well, first of all, my question is there any application of your result? Like, for example, do you know any good examples of this differential algebras, right, with weight lambda? Any good example?
Yes, I showed that. In fact, I think the different. Which maybe I should go faster. Yes.
Mm-hmm.
Wait a minute, sir. So here, so you have the forward backward differential operator, a difference operator in this one. This is somehow differential operator over to +1 or -1, if you like.
Mm-hmm.
So there are also some in paper of Don Rilke. In fact, he mentioned the so-called Ito differential, but I never found it in the literature.
Mm-hmm.
I think this is
but
somehow.
You also mentioned in your theorems that you will be able to find. Yeah.
Yes.
Mm-hmm.
Please.
You also mentioned about the Kozul dual, right? Kozul dual yes. Cooperad, right? For the operad over differential algebra with lambda, right?
Yes. Yes.
The problem is how can you say about Kozul dual if it's not quadratic?
Yes, I think quadratic the algebra case. In general, if you have a Kozul algebra, you have a Kozul dual algebra, co-algebra, or Kozul dual algebra. Yes. In that case, you usually will ask the correlation to be quadratic. But even in algebra, you can somehow define the generalized Kozul dual, even this algebra is not quadratic. In general, you take something like this. So for example, A is TV over I. I mean, okay, this is TV over I. So you can consider the top KK, the top group is KK. Top KK, you know it, the top group of KK. And this top KK will have an A infinity co-algebra structure. Yes, of course, under some finiteness condition. For me, top KK together with this A infinite co-algebra structure will be called Kozul dual co-algebra of this algebra, which are not Kozul. So this is the same philosophy here.
Okay.
So I know that in fact this diff, this operator diff is not Kozul. But as in algebra, we can I can stand sort of the generating part of this overhead of homotopy differential algebras as the so-called Kozul dual something. So in a generalized sense, I call this homotopy copart as the Kozul dual of diff. So I know this is not a wide accepted notion. I should say, yeah, you're right.
Okay. Other questions? No other questions?
Yes, I just have a remark. I thought a lot about this kind of objects, but for properads, yeah, for algebraic structures where you not only have a product but also a co-product, yeah, and so would be very interesting to know how this kind of method generalizes to properads.
Yes, it's a very interesting question. I think in June in May I was in Paris. I met Martin Marco. The property of bialgebra, associative bialgebra. This is rather difficult problem to find the Kozul dual homotopy property. If there is something like this. He told me that in fact many people working on this problem, but yes, you're right. In fact, for example, for Lie algebra, this is considered proper. I think this is shown by Guodong Zhou. For associative algebra, it's an open problem. I should say. Yes.
Yes. Yeah.
But I think that here, I found this example for differential algebra or Rota-Baxter algebras. So, come here. I'm so lucky to find it. I should say that.
Yeah.
In French, par hasard.
Very good talk. Thank you.
Thank you.
Thank you.
You the question? Okay. Thank you.
Okay. No, then let's thank our speaker again. And
okay, thank you very much. Okay, thank you very much.
Okay.
So,
okay. Good night, everyone. Yeah.
Good night.
Bye.
See you. Okay. Bye.